Okay, there are several things that we kind of want to sort of summarize and organize our thoughts on. And specifically, we're talking about properties of polynomial functions. These are all things that you should have seen in the last examples that you've been working through, that we have worked through together. First of all, if you have a polynomial function with degree n, there are going to be n roots or n zeros of that function. If you have a quadratic function, there are 2 zeros. If you have a cubic function, there are 3 zeros. If you have a fourth degree function, there are 4 zeros. Those zeros might be rational numbers, might be irrational numbers, might be complex numbers. The other observation I hope you've made is that when you do have complex roots or zeros, they come in conjugate pairs. If you've got a plus bi, that's 0. A minus b, I also has to be a 0. In our the last example that I worked and recorded for you, we had 2 plus 3i was one of our zeros, and 2 minus 3i was also a 0. That's always going to happen. And then the third thing we want to talk about is the linear factorization theorem, which very simply says if you have an nth degree polynomial function, you can write that as a product of n linear factors. Those linear factors are going to they're connected to the zeros. So in our last example, our function was x to the fourth minus 6x cubed plus 22x squared minus 30x plus 13. And we found that the zeros were x equal 1, and that was a double 0. X equal 2 plus 3i, and x equals 2 minus 3i. Well, if you know what the zeros are, every 0 corresponds to a factor. So the linear factorization theorem says that I can write this as the product x minus 1, and you can write that as x minus 1 multiplied by x minus 1 or squared. Tell you what, either way is fine. And then x minus, be careful here, 2 plus 3i, and x minus the 0, 2 minus 3i. Now the one thing that's left out right there is that there is a lead coefficient out in front of this function. That lead coefficient will match whatever the lead coefficient was in the original function. So in this case it's a 1. You don't really have to write it. But you need to understand that a polynomial function can always be written in the form some coefficient times x minus the first 0 times x minus the second 0, and so on and so on and so on until you get x minus the nth 0. Now, how do we use these ideas? Why is that important for us to think about this all together? Well, what if you're looking for a function? We know we have a third degree function that we're looking for. And the zeros of that function are -3 and I. We also know that in this function it is true that f of 1 is equal to 8. Now stop and think. First thing, how many zeros should there be in a third degree function? Well, there should be 3 zeros. We're only given 2 of them. So you need to stop and think about what does that third 0, what might that third 0 be? Well, I is like the complex number 0 plus I. So 0 minus I has to be the missing 0. So if we know that, then the function we can write can be f of x is equal to some coefficient a, we'll figure that out in a minute, times x minus negative 3 times x minus I times x minus negative I. 3 factors, each connected to a 0. Now, this is when f of 1 equals 8 becomes important. If you plug 8 in for f of x and 1 in for x, that's going to allow you to solve for the coefficient a. Okay, now be smart about how you do this. Don't make it harder than it needs to be. Multiply these two factors together first. You're going to end up with 1 squared minus 1. No, 1 squared plus 1. Sorry. So we're looking at 8 equals a times 4 times 2. Solve that for a. We end up with another example where the lead coefficient is 1. So our function, f of x, that we're looking for here is 1 times x plus 3 times x minus I times x plus I. And if you want, if you're offended by those complex numbers there, or the imaginary numbers showing up there, you can write, you just multiply those two factors together and get a quadratic. It will be x squared plus 1.